So our next presentation topic is retrofit and rehabilitation strategies with advanced fiber reinforced polymer composites. And our speaker is, I am very happy to introduce her. Our speaker is Dr. Shreya Vemuganti. She is a tenure track professor in civil engineering at University of Oklahoma with a PhD from the University of New Mexico. Her research focuses on 3D printed fiber reinforced polymer composites for infrastructure, including polymer matrix nanosynthesis, bridge deck overlays, and strengthening method for concrete elements. She has secured over 1.4 million in funding from agencies like ODOT, NSF, and USDOT. Vemuganti is an active member of ACI 548 and has been involved in multiple international polymer concrete congresses. In 2020, she won the Ralph Poe Junior Faculty Award. So once again, welcome Shreya.
Thank you again, Aparna. I'm happy to be here. It's very tough to follow Tariq, but I'll try to do my best to keep the audience engaged. Good morning, everybody. I hope you're having a great morning. It's Central Standard Time here, so we're still at 11 a.m. But so good afternoon to a lot of the others. Today, my presentation is taking a little bit of a different approach because I'm going to be focusing more on the polymer matrix itself that is very essential for fiber reinforced polymer composites. And in doing so, I will enlighten or share the information that we have based on our research and different kinds of experimental investigations into this polymer matrix for the FRP composite. Little bit of a background about me. I'm at the University of Oklahoma here, finished 3 years as a tenure track assistant professor. We have a very dynamic structures group here at OU. I have a great team of students working, so all thanks to them for all the work that I will be presenting here. I also have some part of work presenting as a PhD student at the University of New Mexico, so I had some projects there too, so I want to share that as well today. Our lab is the Innovative Materials and Methods for Emerging Research in Structural Engineering, our Immerse lab, and we'll dive into the topics for today. So the primary objective, or one of the primary objectives of our lab is to enhance the micro and macro mechanical behavior of FRP composites. These are made with two types of polymers, which are both thermoplastic and thermosetting. So we're going to dive into some thermoset-based FRP composites and thermoplastics-based FRP composites. These enhancements or the micro and macro changes that we are observing are due to design or compositional alterations. So in thermoset-based, I'm going to be discussing about some protrusion-based and vacuum layup-based FRP composites that have these alterations. And in the thermoplastics-based, I will be shedding some light on the 3D printing-based FRP composites. So each of them have different kinds of alterations that I'll be showing you today and what information we have. So compositional and design-based alterations. So if we come to just the polymers itself, polymers are a very vital component in the fiber reinforced polymer composite itself. They protect and transfer the load between fibers. These materials, because FRP is a composite, it's a combination of these two materials, which is the fibers and the polymer matrix. So if you look at a macroscopic scale, to form new and useful materials with enhanced properties, we don't necessarily just concentrate on one of these components. We have to be able to understand both these components. So most of my presentation is focused on that polymeric matrix, which is the protection component as well as the transfer of load component. So coming firstly to thermosetting polymers. Thermosetting polymers are those polymers, if you look at polymeric chains here, we have molecular chains that are cross-linked through chemical bonds. they cannot be reversed or they are not reversibly softened. So that's why also they cannot be bent easily on site. So that's why you see a lot of pultruded bars made with thermosetting polymers. They cannot deteriorate irreversibly at elevated temperature. So their chains are really very strongly interlinked. These are the ones that are commonly used in infrastructure. And some of the thermosetting polymers, the examples will be epoxies, vinyl esters, polyesters, and things like that. If you come to thermoplastic polymers, though, these are very different kinds of polymers which have actually strong bonds within the chain molecule. So if you see strong covalent bond within the chain molecule, however, the chains itself are held by weak van der Waals forces. The covalent bonding is only strong within the chain molecule, but are held together by weak polymeric chains. That is why these molecules can actually easily slide past one another based on elevated temperatures. So they are reversible. They can be softened easily. So that's why these thermoplastic polymers are one of the very famous polymers used in 3D printing applications, where you are looking at a filament-based melting approach where the polymer has to get deposited on a print bed. So if you look at this microscopic images here taken through SEM and PEM, we have these five fibrous materials here, which are the fiber component of an FRP composite. But if you look at the entire composite itself, you have these fibers poking out of a polymeric matrix. And in this research, for the thermosetting polymers, I will be primarily focused on the polymeric matrix. In the thermosetting polymers, the way we are proposing compositional alterations and the research that we've done primarily are related to addition of fillers. So this goes back to the question that one of the audience members has asked, Tariq. We have carbon nanostructures that are very high in covalent bonding because they're made of graphite sheets that are basically just turned into cylindrical, hollow cylindrical tubes. So these carbon nanostructures, one of them being the very famous carbon nanotubes, are extremely strong materials. Though they are at a nanoscale level, their modulus can go as high as 1 terapascal. So very high strength, high stiffness materials, these carbon nanotubes. And there are different types of carbon nanotubes. So this is a single walled carbon nanotube where the graphite sheet is made into a cylindrical tube of just one shell. These are multi-walled carbon nanotubes where there are multiple shells inside one another held together by weak van der Waals forces. These carbon nanotubes have proved to be very effective in the different kinds of alterations that we have achieved here, which I will be sharing now. One of the very primary things we've seen with bars, for example, is the silane sizing agent on the glass fiber or carbon fiber bar itself bonds really well with the functional group on the carbon nanotube. So the surface treated carbon nanotubes really bond well with the silane sizing agents of FRP composites. So that's why we're seeing all the different kind of improvements that we are. So for this particular project, and the paper right here can give more information on this. This is the work done in University of New Mexico with me as a PhD student. We set up a lab scale pultrusion method where we have this epoxy vinyl ester resin bath, which has fillers in it, which are carbon nanotubes. The way to achieve that kind of good homogeneous dispersion of these fillers is through two methods called sonication and mechanical stirring. That helps a more homogeneous dispersion by breaking those weak van der Waals forces and trying to lessen the number of agglomerates there are, because with filler materials that dense, you tend to have more agglomerates. With a preformed die, now we're looking at a number 3 bar. We have a heated die here and the bars coming out. This is more of on-site picture that you can see. We have glass fiber rovings that are being pulled and tensioned into this vinyl ester resin bath. The resin itself is translucent color, but because of the carbon nanotubes added, you see more of a dark color. Once the glass fiber strands are being pulled into this resin bath, we have a preformed die which is heated, and the strands are pulled out, formed into this number 3 bar cross section, and a pulley is basically pulling those bars out. So in this kind of a method, we were able to actually alter that polymer matrix that is used to make pultruded bars. This is a small laboratory section, laboratory scale test setup. But the resulting bars basically were tested for different kinds of mechanical properties. For the resin itself, we wanted to make sure that it's very suitable for pultrusion, and for that the flowability should not be affected that much. When we understood the shear stress versus shear rate, so rheological measurements, we saw that the shear stress was not highly affected with corresponding to shear rate. So the flow of the resin itself is not highly affected by the addition of these pillars. If you see this picture here, you have the plain pultruded bar without any fillers or carbon nanotubes, and you have this right section with carbon nanotubes. So you see some spread of the carbon nanotubes through the section of the bar itself. Trying to understand the mechanical properties, doing a tensile test, we achieved about 20% of improvement in tensile strengths. If you see more of the failure mode, from a brittle, very explosive kind of fibrous failure, which is broom type as described in ASTM, we see a lesser broom or a less explosive kind of failure in the FRP. Modified with carbon nanotubes. Comparing the shear strength itself, this is interlaminar shear, so we can comment on the bond that was created due to the addition of carbon nanotubes. We saw a very good improvement of up to 110% of increase in shear strength when you look at the just plain pultruded bars without any carbon nanotubes, and when compared to with carbon nanotubes pultruded bars. So these are the two improvements we saw. Of course, this work has more information that we seek. For example, the bar sizes, what is the alteration affecting due to the bar size difference. There's also other tests that are very important to kind of extend this work into more additional information. So that is one part of it. When we come to vacuum assisted hand layup, this is some of the work that we've been doing with my master student here in University of Oklahoma. We wanted to really understand how vacuum assisted tapes or strips can be affected with these carbon nanotubes. More importantly, in systems with externally bonded FRP, where peeling is a very possible failure mode. So to understand that, we performed an ASTM peel ply test. For that, we basically bonded 2 layers of carbon fiber with these carbon nanotubes, and we performed these tests on a peel type specimen. The specimen is more evident in this particular picture. If you see, it's more like a T-flange. And the peel is obtained by using a tensile test setup and pulling one end of the flange. So by pulling that one end, we basically understand how much force is needed to pull one layer of the fabric from the other. So if we see in that context, depending on different percentages of carbon nanotubes and also curing temperatures, we saw that a functionalized carbon nanotube made polymeric resin for vacuum-based layup can increase the adhesion by 130%. The interfacial adhesion strength, which is also referred to as the peel strength, increased by 130% when you compare it to a non-nano-modified polymeric resin. So that FRP strips were very important to understand how peel strength can be affected. So we looked at tensile capacities, shear capacities, and now interfacial adhesion strength. If we look at how these nano modified polymeric resins show us the nanotubes, we performed some SEM investigations. Because these CNTs are highly dense particles, it's very important to achieve a good dispersion, and several factors play into effect. And this paper is one of those effects, studying that relation between temperature or heat on the energy that it needs to cure well and disperse well. So if you see, this is one carbon nanotube here poking out from the polymeric matrix of approximately a scale of 20 to 30 nanometer in diameter and 15 to 20 micrometer in length. And so coming back to thermosetting thermoplastic, we talked about thermoplastic where there are extremely strong bonds within chain molecules. However, they are held by weak covalent bonds. And the 3D printing is a very well-known, renowned technique to use these thermoplastic polymers. What we did is we looked into thermoplastic-based FRP composites and how we can alter design to actually achieve enhancements in its macro mechanical properties. How are thermoplastic polymers even made? We use filaments basically in the 3D printer. These are made using filament makers, and those filament makers basically take polymeric pellets. Those pellets can be, nylon or PEEK or PET or whatever. Sometimes these pellets also have some inclusions in them, for example, chopped fibers to improve the bond capacity or strength of these thermoplastic polymers. What we used is a market-approved, mark-forged tabletop kind of 3D printer, which has the capability of a dual nozzle, which more importantly means that it is able to print both thermoplastic and a fibrous material on the same layer of the specimen or the composite. So if you see here, this is a spool that contains the fiberglass, which looks like this, the transparent fiberglass coming out of that nozzle, and it can be basically print on this print bed here. The capability of these kinds of printers is that beauty of achieving different fiber orientations. We know that highly anisotropic materials such as this one are highly direction dependent. Their stiffness and strength changes with direction. So the orientations are something that we can achieve with very high accuracy. And I can claim that because microscopic investigations that we've done show that if you're trying to achieve a 0-degree composite, so the fiber laid in a 0-degree fashion, you will achieve with 99% accuracy 0 degrees. If it's a 12-degree, so an arbitrary angle, it's still a very, very accurate layup of the fiber. So these are 3D printed fiber reinforcements at different angles. That in a typical system of reinforcements used in civil infrastructure, we have steel, of course, which is a very robust material in terms of strength, and longevity is right now with aging and everything and the environmental exposure. We have a lot of problems with aging infrastructure, including steel. But the strength, even though nominal for, let's say, a mild steel, we have a very good failure strain of above 5%, which makes it really ductile and great for civil infrastructure. If we look at CFRP and GFRP, we have, of course, very linear elastic behavior for high strength composites. And so I'm strictly talking about unidirectional, where the fibers are going only in one direction, preferably in line to the tensile load. We have low ductility, so more linear elastic to failure, brittle, abrupt, and broom-like. The strength, of course, is very high for CFRP. lower strength for GFRP, but a little higher in strain. But an ideal or a target FRP system would be something that maybe behaves like a steel, but still with that maintaining that high strength and ductility. So keeping this in mind, we try to look into possibilities of altering the design through this modern technology, which is 3D printing or additive manufacturing or layer on layer building, to use this different kinds of orientations that we saw and understand how that can affect maybe a delayed failure or a progressive failure. So to keep that more in terms of how the specimen looks, or a strip if you build an FRP strip, this strip now will be a layup that consists of different laminas, but those laminas are going to be aligned at different orientations to the tensile load. And that is based purely on mechanics, where you have load factors or load fractions that vary with this direction dependent properties, which are primarily modulus of elasticity and the area the fiber is occupying. So you have this mechanics related formula for axial stiffness and achieving that kind of a load fraction, where we are saying that if one lamina fails, the other should be taking the residual load. So to achieve that smooth transition, we use 3D printing and different multiple orientations to get low load fractions, because that would mean the transfer of load is happening in a more smoother or non-abrupt way. So if you look at this particular strip, an FRP strip, it would consist of different orientations. For example, the red is related to a 0 degrees. The white strips are related to a 12-degree oriented fiber. The black strips are related to a 24-degree, and yellow in this particular design is related to a 30 degrees. So compared to 0, which is the traditional way of building an FRP composite, we have other directions that are with respect to 0 at 12, 24, and 30 degrees orientations. So these were 3D printed, and the mechanical properties, especially in terms of tensile strength and ductility, were understood. So if you look at the stress versus strain in an ASTM D3039 setup, we've seen that these different orientations bonded together in different ways have very unique behavior. If you see a bonded, which is basically saying that all these orientations are stuck together in the layup that I just showed. We have high strength, obviously, because the shear transfer is very effective. The bond is very strong between these different orientations. But you see more of a progressive failure, which is step-by-step failure. And that is happening purely due to the modulus of elasticity of those orientations and how much of an area of the composite that orientation is occupying. If you see an altered bond, again, this presentation, I will be in very detail in the next ACI next meeting that we'll have virtual seminar. I will go much deeper into these different kinds of bonds, but because of just like an overview, I kept it short for this round. If you look at another kind of bonding, we still have some kind of progressive failure, but you can see that the stiffness has decreased and the strength has also decreased. In a different unique bond where you have no bonding between these different orientations, you have a very good improvement in the progressive failure, where basically that delayed failure is going up to 5%, although at a compromised strength and stiffness. So the target would be in 3D printing, if that is really so effective in achieving delayed failures, the ideal situation would be with 3D printing to achieve that kind of a unique bond between these composites, where you have a non-compromised strength and stiffness, while providing that delayed failure mechanism or progressive failure mechanism. If you look at ductility index, which basically what we're saying is the portion of a linear elastic behavior versus the portion of an elastic behavior. That ductility index, if you look at the new ductile GFRP that we are referring to here, pultruded GFRP, which is traditionally unidirectional in a 0-degree orientation, is at least 95% less in ductility index because it's highly linear elastic to failure. If we see A36 mild steel, it's still 70% high with ductility, but the new alterations or new kind of design approach can maybe get that GFRP into becoming more ductile and maybe comparable to that A36 mild steel. So this is again a comparison between stress versus strain. You see this pultruded GFRP, which is highly linear elastic to failure, very strong, good stiffness. You see the steel, which has a reasonable yield strength with high stiffness. And here is the new GFRP with those orientations and altering the bond, achieving lower stiffness and strength, but very high ductility or ductility index compared to a pultruded GFRP. Failures of these particular composites, again, if you look at a simple unidirectional that looks like this has also been 3D printed to make sure it's an apples to apples comparison. If you look at drop 1, 2, 3, 4, 5, this is the new ductile GFRP where one layer failure doesn't necessarily affect the other immediately. That is why we see that one layer failing and we see still the residual load being carried by the other layers, and then you have failure in the other layer. Then in drop 3, you have the third layer that is causing failure. You have drop 4 where you see the last layer here subjected to failure. Drop 5, there is failure in the rightmost layer. This is in terms of another bond where we see only certain drops. So the highest number of drops is achieved in this fully debonded configuration. So hopefully 3D printing, or we can achieve some kind of filamentous debonding where we are still able to do that shear transfer, but not in an abrupt fashion, so as to improve the delayed failure or progressive mechanism of FRP composites. We've taken these FRP composites and put them in concretes because our focus is primarily civil infrastructure. One of these composites, one of these concretes here is Portland cement concrete, and the other here is polymer concrete. Now, in the polymer concrete, we have used methyl methacrylate based polymers, and we've seen that this polymer concrete has the potential to seep into the gaps that are between these FRP composites, and as low as 94 micron, you can see. And that has helped a very important behavior, which is deflection at peak load. You see that a Portland cement concrete with this 3D printed multi-directional when compared to unidirectional that is 3D printed and a conventional unidirectional, the deflection is almost 100% increase. In a polymer concrete as well, you have very high deflections when compared to a non-reinforced or a unidirectional or a 3D printed unidirectional. So in these two different kinds of concretes also we've seen behavior, and this is also published. The list of all the papers that I've talked about only in this presentation are right here. The yellows are my highlighted students, and the others are my PhD work, which I am also trying to keep that heritage here in University of Oklahoma. You have a reference to all these papers in my Google Scholar link here, but if you have any further questions, I'm more than happy to answer your questions over Zoom or over emails or anything you'd like. I do want to take a moment to thank our funding agencies because this work is not possible without any of them. So thank you everybody listed here. And I'm very happy to take any questions now at this point. Thank you for your patience and have a nice day.
Shreya, thank you so much for your outstanding presentation. You did went to the polymer matrix, and that was really beneficial. So our first question is, to what void percentage ratio you were able to get with this manufacturing process?
So that's a great question. If you're talking about the pultrusion process, our volume fractions were 55 to 60% range. That's what the volume fractions we've achieved. The paper that is linked has those numbers, and you can go back and check them and see. I think Aslan has different volume fractions, but I have seen 60% volume fractions in those as well. If you're talking about the others, which are 3D printed, one thing to remember is the volume fraction measurement in the 3D printed will be slightly altered because a 3D printed filament itself has polymer in it. So even if it's a fiber filament, the only way it can be melted is because of a polymer presence. So that volume fraction is going to be completely different. And the way we did that actually is by burning and everything. This is a thermoplastic, so it was quite a bit of challenge. But what we did is we went back and did a thermogravimetric analysis on the fiber itself, which is the filament. That filament itself has 50% of polymer. So we're looking at a very low volume fraction in 3D printed composites. I'm really crossing my fingers that the technology improves and advancements help us to achieve a higher volume fraction of the fiber filament. If that happens, if we're looking at 75, 80% of the fiber filament to be actual fiber, you will see much different values in terms of strength and stiffness. So in the papers that I've listed here, that is one of the limitations of not necessarily this work, but the advancement right now in the stage we are in additive manufacturing of FRP composites, that the fiber filament itself needs to improve in volume fraction.
Great. Thank you. Our next question is, the polymer matrix which you have been working, has that been implemented for any retrofitting or rehabilitation structures? If not, do you have any plans in the future?
So we have Oklahoma DOT here who are amazing in this collaboration between research and industry. Right now, in the stage we are in, we'd like to publish more work. I'm 3 years into University of Oklahoma as an assistant professor. The pultrusion paper, though, and the work that is, it is a patent pending application. So that really eventually we hope that it gets into the industry as an actual bar. But the vacuum assisted wet layup and different elevated temperatures, I want more and more work from my team to come out there and increase awareness of these kind of carbon nanostructures in civil infrastructure FRP composites. I'm really hoping that we can have this Oklahoma DOT collaboration. We've already dealt with some projects with them. Maybe this can be a future potential, but my primary focus is to get so much work out there that other people recognize the potential of this and reach out for application into actual retrofit areas. Yeah.
Great. Thank you so much.
If anybody is interested in that 3D printed FRP composite, the ductile one, we have more coming up in more detail on October 17th.
Yeah. So just to be curious, so this polymer matrix, you said it's more flexible for 3D printing. So is there a reason why it's more flexible for 3D printing, or you have designed it in a way that it's more flexible instead of using for other purposes?
Sure, yeah. So these thermoplastic polymers, so thermosets and thermoplastic are the different kinds of polymers that exist. Thermosetting polymers, as I mentioned, it's primarily the bond. So those polymeric chains, within those polymeric chains, if there is a strong bond, but they are still linked with each other in a weak kind of bond, what happens is when high temperatures are available, these can be reversed. So why they are important in 3D printing is, and I'm not saying 3D printing is the only way to use thermoplastic polymers as well. 3D printing is one of the ways, but it's a very good way because you have so much control on this polymeric resin. So in 3D printing, what happens is they use these filaments of thermoplastic, and the nozzle itself, which is right here, this is the print head and this is the nozzle. That nozzle heats up to, for example, nylon, it heats up to about 270 C. What that does is it enables sliding of the polymeric chains with each other, and that is why the polymer from a hardened state, it becomes into a molten state. For epoxies, vinyl esters, polyesters, which are thermosetting, this is not possible because they are held with such strong polymeric chains that they cannot be melted easily or they cannot be softened easily because their chains cannot be broken easily. So that is the only reason. So it completely comes down to the materials and the micromechanics, or even deeper into the polymeric chains, covalent bonding, the atomic structure. So it comes down to that level.
Great, great. Thank you so much. I think this was a very nice presentation, and we thank you again.